In this video, we will learn to create syntax and semantic analyzer using Bison. In our last video, we wrote Flex code and built a lexical analyzer for our language Simple C. In that video, we created ssc.tab.h ourselves and wrote our main function in the lexical analyzer. This was because we wanted to create the lexical analyzer as a standalone program and thoroughly test it. However, in reality, Bison will automatically create the header file ssc.tab.h and our main program should reside in the Bison. Bison will take care of calling the lexical analyzer for the next token and placing it into the abstract syntax tree immediately upon receiving. Instead of generating all the tokens first and then passing them on, Bison allows us to work on continuous flows of tokens. This approach, working with the stream of tokens, is faster and more memory efficient. Let's jump in and start creating Bison code. I open my terminal. In my ssc directory, now there is only two files. Number one is ssc.l, which is flex file, and number two is testfiles.ssc. This file contains source code of our language for the testing purpose. In this video, we will be creating ssc.y, that is a Bison file where the Bison code will reside. Just like flex file, Bison file also has three different sections. First section is definition section. Second section is rule sections, which is obviously the most important section. And in the third section, we will write our C code and also we will have our main function. As explained previously, our main function will reside in the Bison file. And the Bison file will be calling flex for the next token and then inserting that token in the abstract syntax tree. So let's start by moving the main function from the flex file to the Bison file. The main function will remain the same in general. However, instead of calling yylex, we will be calling yyparse. And yyparse will be calling yylex by itself. We must include the declaration of yyparse and yylex functions in the ssc.y. I'm also using yin in my main program. It is a built-in flex variable. I must include that variable as an external file pointer in ssc.y, otherwise my code will not compile. In the previous video, we generated the ssc.tab.h files containing all of our token IDs and a union to store token values. However, that file no longer exists. Now we require token IDs that are shared between Bison and Flex. To achieve this, we utilize the %token directive in our Bison file, followed by the name of the constant variable that will hold the token ID. Bison will then automatically generate the ssc.tab.h file with the corresponding variable names and assign token ID to these variables, ensuring that Flex and Bison use the same token IDs. Following that, I employ the %union directive to define the names and types of element contained within the union. This union serves as a container for token values, including identifier names and double literals, etc. The creation of union and tokens IDs through these directives facilitate communication between Bison and Flex, establishing a shared data framework. The variable names specified with %token directive represent the terminal symbols of our context-free grammar. It is important to identify the start symbol of our grammar using the %start directive. In our case, the start symbol is labeled root. Following this, we begin writing our context-free grammar and linking each grammar production with C or C++ code. This process is known as syntax-directed translation. In Bison, when defining a production rule, we first indicate the non-terminal symbol on the left-hand side, followed by a colon. Then we list the different alternatives for that non-terminal, separated by the pipe sign. Finally, each production must terminate with a semicolon, indicating the end of the rule. In root's production, we have only three alternatives: print S for printing strings, print D for printing doubles, and assignment. That is because our simple C language only includes these three kinds of instructions. However, we need a way to handle situations where there are several instructions corresponding to each alternative in our source code file. To do this, I have added a new epsilon rule at the beginning, which is marked with a comment. Then, for each alternative, I have added root again at the right hand side. This way, we have created a write recursion and thus can handle a source file having multiple instructions of any of those three alternatives. For each alternative in my context-free grammar rule, we can write corresponding C code. While I plan to write more comprehensive code later, for now I have added a macro named debug Bison with different parameters for each rule to facilitate testing. Now let's write the productions corresponding to each alternative of root. Recall that the printS function starts with an opening parenthesis, followed by a string literal, a closing parenthesis, and ends with a semicolon. We use this same structure in our context-free grammar rule. Note that all the tokens whose ASCII values were sent from Flex can be used as characters in single quotes. Therefore, in our rule, we use single quote for the parenthesis and semicolon. In the code corresponding to the rule, we again use debug Bison function with a unique parameter. Next, I write the rule for print D function. It is similar to the printf function but takes either a double literal like 700 or a double identifier. We write similar code but with a non-terminal named term as the parameter. In a subsequent rule, the non-terminal term is defined to match either a double literal or a double identifier. We continue to use the debug Bison macro for each rule, ensuring each call has a unique parameter. Next, I write the rule for assignment. Let's quickly recall what an assignment is. An identifier followed by an equal sign, then an expression on the right hand side, and ending with a semicolon. We follow this exact sequence in our context-free grammar rule. In the corresponding C code, we call the debug Bison macro as usual. Note that expression is a new non-terminal that we will define next. The expression non-terminal can take several forms. It can be a simple term, an addition of two expressions, a subtraction of two expressions, a division, a multiplication, or an expression enclosed in parentheses. I understand that the definition of expression is left recursive and is ambiguous. But don't worry, I will address these issues later on. First, let me review all the rules one by one to ensure that there are no mistakes. In the root prediction, I missed a pipe sign after the epsilon alternative. Additionally, the printf and printd predictions are not correct either. I need to include the talk printf and talk printd tokens at their beginning to make them work perfectly. After making these corrections, my rules are now error-free. Yahoo! Now I can focus on making the grammar unambiguous. While it is possible to introduce several additional predictions to achieve this task, the resulting grammar would be much more complex. Instead, Bison provides us with %left and %right associativity directives, which simplify this task. In our case, I use the %left directive to specify associativity and precedence for operators. I declare %left plus minus to indicate that the addition and subtraction operators are left associative and have the lowest precedence. Next, I declare % multiply and divide to indicate that multiplication and division are also left associative but have higher precedence than addition and subtraction. Finally, I declare %left with closing and opening parentheses, which effectively give parentheses the higher precedence. These directives give the parser additional information, ensuring that our seemingly ambiguous grammar operates unambiguously. Cool, yes? Lastly, I check my definitions section to ensure everything is in order. First, I include studio.h and stdlib.h because I'm using the printf and exit functions respectively. Secondly, I notice that file is not in all caps, so I must change it to all caps file, otherwise my code will not compile. Finally, I need to write the YY_error function, which used to be in ssc.tab.h, but now it is nowhere defined, and this function is used by both Bison and Flex. I have already declared it as an extern in Flex, so I define it here. Now everything is in order, and we are done with the first iteration of our Bison code. Let's test it and see it in action. In order to compile everything, first I should use Bison command. I write Bison -t ssc.y. -t is important because -t will produce ssc tab.h. So please use -t, otherwise header file will not be produced. After producing the header file and compiling Bison, next I will compile Flex. I will write flex ssc.l. Finally, I have all the C and header files. Now I have to compile them using GCC or Clang. I prefer Clang++, so I write Clang++ static.c, and my code has compiled without any errors. Then I run a.out with the test file, and it has produced desired output. Let's now build a fully functional language by implementing C code for each context-free grammar protection in Bison. The functions we create in this video can later be easily replaced with equivalent LLVM function calls. Our terminals, also known as tokens, will be used to store data provided by Flex. To achieve this, we first need to define the type of each terminal symbol. The types must be the same as declared using union directive. I assign the type identifier to the terminal talk identifier. Similarly, the terminal talk double literal is of type double literal, and the terminal talk string literal is of type string literal. Next, we specify the types of non-terminals using the type directive. In this case, the non-terminals term and expression both are assigned the type double literal, as they will store double values. With these definitions set, we can now write C code that will enable any program written in our language, simple C, to function properly. Let's review how to access terminals and non-terminals in your C code. Consider the protection expression producing expression plus expression. The left-hand side non-terminal is accessed using double $sign, while the right-hand side symbols are accessed with $1, $2, and $3 corresponding to their order in the protections. So to add the two symbols on the right hand side and store the result in the left hand side expression symbol, the code should be double $sign equals to $1 plus $3 semicolon. This is a C++ or C code where we are using special symbol for accessing terminals and non-terminals. For better readability and reusability, it's a good idea to encapsulate this logic within a function, which we can later reuse also for LLVM code. Therefore, I create a header file called ir.h and start writing my function, which will be called for 4 different expression protections. Later on, this same function will be modified to support LLVM IR. My function perform binary operation has three inputs. The first two are of type double, representing the operands of the expression productions. And the third input is the operator, which specify the operation to be performed on the first two inputs. After performing the operation, the function returns the result as a double value. Inside the function body, I use a C switch statement on the operator, which could be plus, minus, multiply, or divide. I write different cases corresponding to each production. In the case of plus, I add and return the result. In the case of minus, I minus the first two inputs and return the result, so on. Next, I call this function from the four expression productions and save their result in the left hand side expression symbol using double $sign. For the production expression producing term, I write in the C code double $sign equals to $1 followed by a semicolon. Even in the case of LLVM, this same code will suffice, so I am not creating a new function in this case. Similarly, for the production expression producing start parenthesis, expression closing parenthesis, I write C code that assign $2 to the double $sign followed by a semicolon. You may be wondering why, while writing my C code, I have ignored the parentheses. This is because we have already stated that parentheses have higher precedence over other operations by using the left directive, so it is safe to ignore them here in the C code. Next, let's write code for the production of the printS non-terminal. We call a function named print with two inputs. The first input is the printing format, which in this case of printS is %s\n, and the second input is the string literal to be printed, which I can get from the production using $3. In the ir.h file, I write the definition of the print function, which take two constant character pointers as input and uses them to call the cprintf function. The C code corresponding to the productions of the printd non-terminal is similar to the code we have written for printS. However, in this case, the second parameter will contain a double value. Therefore, in the ir.h, I create another print function using function overloading, where the second parameter is of type double. Next, let's write C code corresponding to production assignment producing talk identifier equals to expression semicolon. First, let's understand what it desires in this case. We need to save the value of the expression, which will be of type double, in a specific identifier so that we can retrieve it later and use it. If we simply store it in the non-terminal talk identifier, it will be overwritten by the next execution of production. So we need a data structure to store the values of identifier. In compiler design, we call such a data structure that is used to store temporary values as symbol table. It is a map, a key value pair where the keys will be names of identifier and the corresponding values will be the double values of these identifiers. Now in the C code corresponding to the production assignment producing talk identifier equals to expression, we call a function set value in symbol table, which will take two parameters. The first parameter is the name of identifier, whereas the second parameter is the double value to store in the identifier. Next, in the ir.h, in the body of this function, we simply update the symbol table map using the input parameter of key and value pair. Next, we write code for the production term talk identifier. Here we need to fetch a specific identifier data based on its name. Thus, we only have to get the value from our data structure symbol table and store it in the term using the double $sign. Therefore, we call a function getValue from symbol table that takes input of identifier name and then fetch that identifier from the symbol table map and return it. Finally, for the production term producing talk double value, our C code will be double $sign equals to $1, which will save a double value in the term non-terminal. That's it. We are done writing the Bison code, which should execute like a programming language, but it is not an intermediate representation at all. These functions will be useful for understanding the flow of Bison and replacing them with LLVM IR functions later on. I have written a test program in my SSC file, and let's execute it and see if everything is working fine. And yes, our program is executing and producing the right result. I will upload everything on GitHub for you to download. Please go ahead, download it and improve this project. That is it for this video. Please support my channel using the link provided in the description of the video. I hope to see you around. Bye.